This video is about congruent figures, and you can find it in your text in section 4-1. Here's a definition for you. Two polygons are congruent if their vertices can be matched up so that all corresponding parts, angles, and sides are congruent. So let's take this statement apart a little bit. Their vertices, so if these two triangles are congruent, that means that all three vertices could be matched up and the triangles would actually be superimposed on one another. Suppose I tell you that triangle ABC is congruent to triangle DEF. What I would be saying is I could take vertex A and bring it over on top of vertex D. I put vertex B on top of vertex E. And if I did that, vertex C would automatically line up perfectly on vertex F, and all of the sides would be superimposed on one another, and the shapes would be indistinguishable. So to say that triangle ABC is congruent to triangle DEF means all of these statements must be true. All of the angles that are corresponding, so vertex A and vertex D must have angles that are congruent. In other words, we have angle A congruent to angle D. Similarly, angle B is congruent to angle E. Angle C is congruent to angle F. Not only that, but it's also true that the segments that make up the three sides of these figures must also be congruent. So segment AB must be congruent to segment DE. Let's mark those congruent with 1/. Notice that AB is listed in the same order as DE when we named the triangles. And that's a very important part of when we state that two triangles are congruent. So we're also saying that segment BC is congruent to segment EF. We're saying that segment CA is congruent to segment FD. So if triangle ABC is congruent to triangle DEF, then is it also true that triangle ABC must be congruent to triangle DFE? It looks like they're the same two shapes. I've only named them slightly differently. So you think about it for a minute, whether it would be true that ABC must be congruent to DFE. Actually, it's not true. If we list the vertices of the triangle in a different order, that can change the statement about whether the two triangles are congruent or not. We have triangle ABC here, but now we've named this triangle over here going this direction, DFE. So what we've implied by saying that these two triangles are congruent is that side AB must be congruent to side side DF. AB, we're saying, is congruent to DF. Clearly, that's not true. So something's wrong with this picture, and the assertion that these two triangles are congruent is false. So if we make the claim that two polygons are congruent, we're making a very strong statement. We're saying that every pair of angles in the order that we list the vertices is congruent. And we're also saying that every pair of sides in the order that we name the polygon is also congruent. Let's do an example problem. Points A, B, C, D, E, and F are plotted on graph paper, and two congruent triangles are drawn. So in this problem, we're told that already that the triangles are congruent. What we're being asked to do is name the triangle that's congruent to triangle ABC. We need to fill in the blank here and figure out how to name this other triangle to make it true that triangle ABC is congruent to this triangle. Okay, so let's start with side lengths. On graph paper, it's easy to find this side length, the side length of AB. We can either subtract their x-coordinates, since it's a horizontal side, or we can just count over boxes. 1, 2, 3, 4, 5. It looks like this side is 5 units long. So can we find a side on this triangle that's 5 units long? Just by a quick look, I can tell that side DF is also 5 units. 1, 2, 3, 4, 5. So I'm going to mark that side 5. And so it's true that this side AB is congruent to this side DF. Okay, so it's looking like maybe we could just go around counterclockwise on this triangle, just like we did on triangle ABC. But let's look at something else first before we make that decision. It looks like in this triangle we have a special angle here. You might remember that if we have a square and a line forms a diagonal of that square, then it makes a 45-degree angle. So over here in this triangle, is this a 45-degree angle? Well, side EF is not making a diagonal of a square, so this angle doesn't look like it can be a 45-degree angle. But over here, we do have a side that's making up the diagonal of a square. So this angle is 45 degrees. So now it's looking as if this vertex might be supposed to line up with vertex D. Also, you might remember that to find the length of a diagonal of a square, we can use the Pythagorean theorem, or you might have just memorized that the length of this side is 2 times the square root of 2 if it's a 2 by 2 square. In any case, we can tell that the diagonal of a 2 by 2 square must be congruent to the diagonal of a 2 by 2 square. So I'm going to mark these congruent. Okay, so now we have a lot of clues to how to name this triangle. Triangle ABC, vertex A was named first. So what would correspond to vertex A? Well, vertex A is not the 45-degree one, and it is attached to the side of length 5. So the only vertex in this triangle that fits those qualifications is vertex F. Vertex F is not the 45-degree angle vertex, and it is attached to the side of length 5. So we're going to start naming this triangle with vertex F. What comes next? Well, in triangle ABC, we went along the side of length 5. So in this triangle, we're going to do the same thing. We're going to go F to D along the length of that side that's 5 units long. And we've arrived at the 45-degree angle, which is good because in triangle ABC, B is also the 45-degree angle. So B and D are matching up. And then finally, the only vertex left is E. So as it turns out, triangle ABC, going counterclockwise, is congruent to triangle FDE, going clockwise in this triangle. You try one. Plot these points on graph paper and complete the statement. Triangle ABC is congruent to what other triangle? Now let's try one more example. In triangle ABC and segment DE are drawn on graph paper. Find 2 locations of F, we don't know where point F is, such that triangle ABC would be congruent to triangle DEF. So F is our mystery point, but let's see what we're starting with here. Triangle ABC, the first side of that triangle is side AB, and it looks like here that side is 3 units long. In triangle DEF, the first side is DE, and that side is also 3 units long. So we have 2 corresponding sides here. Okay, now as we go around the triangle ABC, we go A, B, C. So the next side, BC, has a length that is the diagonal of a 2 by 2 square. This side BC must turn out to be congruent to side EF in the other triangle. So what we want to do is we want to make side EF have the length of this diagonal. We also can see that angle B is 45 degrees in this triangle, and that's the middle vertex listed. So angle E should also be 45 degrees. So with that information, I can make a dotted line that would be making a 45-degree angle from E. But wait, I could also make a dotted line over here that would make a 45-degree angle with point E. So it looks like there's 2 possibilities here. We just said that side BC is the diagonal of a 2 by 2 square. So if I'm going this direction, I could make this diagonal, this 2 by 2 square here. If I'm going this way, I would have to make this diagonal. And then finally, I would have to join the final side of the triangle. So it looks like I've made 2 possible triangles where point F could be in 2 different places and still have the statement be true that triangle ABC is congruent to triangle DEF. It turns out that in fact this is possible. There are 2 possible places for F to be, because a triangle that's a mirror image of another triangle is still considered congruent. So triangle DEF named this way, or triangle DEF named this way, would both be congruent to triangle ABC named this way in a counterclockwise direction. You try one. Plot the given points on graph paper. Draw triangle ABC and segment DE, and find 2 locations of F such that triangle ABC is congruent to triangle DEF. For further practice, see page 120 of your book, numbers 15 to 19 odd.